Hello all of you. Welcome to the 22nd lecture in the course on analysis and modeling in chemical engineering. In the last lecture, we started talking about evaporators and we discussed the mass and energy balance on a single effect evaporator. In this lecture, I am going to extend it to multiple effect evaporators and we will discuss two kinds of feed arrangements, the forward feed and the reverse feed, and we will again do the mass or material balance and energy balance for that case. So, just to quickly recap what we have done so far, we have discussed about this evaporator where we have some feed that is converted into concentrated liquid coming from bottom and a vapor going out from top. The feed contains some solute mass fraction XF and the liquid in the end contains some higher mass fraction XL, and we assume that the vapor does not contain solute. It is completely non-volatile solute, and this heating is done by steam that is saturated, available at a temperature Ts and some pressure Ps, and that is condensing inside. So whatever is going out is also this, right? And the feed is at some temperature condition Tf, and there is some temperature and pressure inside the evaporator as well, right? And the equations that we have got for this system was the overall mass balance, the solute mass balance, the energy balance, assuming that there is no heat of solution and there is no boiling point elevation, we can get the solute mass balance as like this. And then we also have a heat exchange equation that is something like S lambda S is equal to UA delta T, and delta T in this case is Ts minus T. So, one of the problems with this system is like we are using this steam to basically evaporate my liquid, and the steam that is coming out is pretty much a liquid. So, this steam is now pretty much useless, but this vapor that is coming out is still hot, right? So, in the end, if my interest is, let's say, to get pure liquid out of this, in any case I have to condense that vapor, right? And whenever I condense that vapor, I will get some energy, right? So, why don't we use that energy for some useful purpose, right? And in this case, for multiple effect evaporator, we are going to use that energy of the vapor to basically evaporate subsequent effects. So, I will attach further effects down the line which will use the energy present in the vapor. So, the idea is to pretty much use this vapor to basically heat up the subsequent effects. That is fundamentally the idea. And the advantage we get from that is now we will again form a new vapor, and therefore, the net vapor produced is much more than the vapor produced in the earlier case, right? Or the amount of solvent evaporated, the net amount evaporated will be larger. Or in other words, what we can also have is we can have higher concentration of the liquid coming out from there, right? So, by doing that, you can imagine I am going to improve the steam economy, because if I am having a single effect, then this steam is giving me certain amount of vapor, and the steam economy is simply determined by the vapor that is produced by the steam that is fed. But by this arrangement which I am suggesting now, we can have, let us say, the same V and some V prime coming from the subsequent effect. So, the steam economy will be something like V plus V prime by S, because this is where I am putting in fresh steam. The subsequent evaporators effects are not using fresh steam, they are using the energy contained in the vapor, right. So, basically we are killing two birds in a single shot. So, we are using the energy that is present in the hot vapor, and second, we are saving the amount of steam required to achieve certain evaporation or certain concentration. So how do we do that? We can do that in two ways. One of the ways is the forward feed. Here I will do pretty much what I have just demonstrated. So we have a feed that enters the evaporator, which I will call now effect number 1, where I am going to use fresh steam to evaporate the liquid. But the vapor that is coming in, this vapor now becomes the heating media of the second effect that is down the line. And now the second effect will again produce a vapor, and I can probably discard it, or I can attach another effect down the line, and we will get concentrated liquid from here that clearly will have higher concentration than compared to whatever we have there, right? So if I am doing something like this, I am doing it in forward feed. Forward meaning that both the fresh feed and the fresh steam are entering the same effect, and I am utilizing the vapor to basically evaporate liquid in the subsequent effects. I can do the opposite of that as well, and I will come to that. But before that, one thing that we have to clearly keep in mind is the operating temperature of the effects now cannot be the same. The reason being that we had earlier some temperature Ts of the fresh steam and some temperature T of the effect 1, the operating temperature of the liquid, and we had therefore a delta T difference Ts minus T, which pretty much provided the energy UA delta T to the liquid here, that pretty much was able to evaporate the liquid in the effect, right? But now the vapor is available at the temperature T only, right? So now let us say if the second effect is operating at the same temperature, now we don't have a delta T available with us. Let us say this temperature is some T and this temperature is also T. Now delta T is 0. So I cannot get any heat exchange by this route, right? So what I can do therefore is to operate the second effect at a lower temperature, right? So let us say this is T1 and this is T2, where T1 is higher than T2. But there is one more constraint that we have, that this temperature must be the boiling point for the liquid, right? So if T1 is higher than T2, how do we ensure that the second effect is also at the boiling point, right? And we can do that by also changing the corresponding pressure. As you know, increasing pressure increases the boiling point, and therefore lowering pressure will lower the boiling point. So let us say if this effect is operating at some pressure P1, this will now operate at some pressure P2, where P1 is higher than P2. And as a result, the boiling point will be T2 here, which will be less than T1, right? So subsequent effect is operating at a lower boiling point, right? And now this is T1 and this is again T1. So now we have a delta T, T1 minus T2, that is positive, and now still heat exchange can take place, right? So that is one of the very important ideas. Whenever we are using multiple effects, the temperature and pressure will decrease as we go to subsequent effects, because I want to use the vapor that is coming out from the given effect to basically become the heating medium for the subsequent effect. And I can only achieve that if subsequent effect or the next effect is operating at a lower temperature, right? So when is it good? It will be good when, for example, we have, let's say, already a feed that is hot, right? So in that case, you can see a hot feed is coming, it requires less heating, right? So clearly this will be very efficient, because otherwise I need to supply a lot of heat, and that I can get only by increasing the steam flow rate, because steam is giving the heat, right? So my S lambda S is equal to UA delta T. So if I require more heat, in that case I have to provide more steam. So if I have hot feed, this is clearly efficient. And one thing that is beautiful in this case, and we will compare that with another system I will talk just now, is there is no pumping requirement. you can see both the feed, the liquid and vapor are flowing in the same direction, and pressure is decreasing down the line. So, since the pressure is decreasing between effect 1 to effect 2, so basically the fluid is going in direction of decreasing pressure, and therefore there is no pumping requirement in this case. So, I can do the opposite of that. Rather than feeding in the same effect as the fresh steam, I can feed in the second effect, right? So, my feed is coming here, and whatever liquid I get from the effect 2, now I am feeding that in effect 1, completely opposite of whatever we have done earlier. Here, the liquid from the effect 1 was entering effect 2, and now in the reverse feed, the liquid from the effect 2 is entering the effect 1, and the final product now comes from the effect 1. In the previous case, the final product was coming from the effect 2, right? What is the benefit of that? Again, for the whatever steam economy benefit we have earlier, the same also applies here, because the direction of the flow of vapor has not changed, right? So, I again have the same idea that, let us say, if this is T1 and this is P1 and this is T2 and this is P2. So, T1 is still higher than T2 and P1 is still higher than P2, because I am using this vapor at temperature T1 to heat up the effect at temperature T2. So, delta T must be positive here in order for this vapor to heat up the second effect. That is still valid. But now the advantage is I can now work with cold feed. Why? Because whatever we have here, that is operating at a lower temperature. So, if I supply a cold feed to the second effect now, I will be requiring it to heat up to a much lower temperature as opposed to feeding it here. Let us say if this is operating at T1 is equal to 120 degrees Celsius and this is operating at 90 degrees Celsius and my feed is at 80 degrees Celsius. If I am doing forward feed, I have to increase the temperature of feed by 40 degrees Celsius, 120 minus 80. On the other hand, if I am doing reverse feed, then I have to raise the temperature of feed to the 90 degrees Celsius only, right? So, by doing that, we can basically reduce the steam requirement if we have cold feed for the reverse arrangement, right? If we have hot feed, we will go for the opposite, because let us say, for example, opposite happens and the feed comes at a temperature of, let us say, 120, but the effect is operating at a temperature of, let us say, 80 degrees Celsius. That is no good, because now we have to basically cool the feed in order to evaporate it, and that again will require energy. Both heating and cooling requires energy, right? So, therefore, if I have hot feed, I will go for the forward feed, and for cold, I will go for the reverse feed, right? And clearly, now we also require pumping, because although the vapor is going in direction of decreasing pressure, the liquid is flowing in a reverse manner. So, liquid is going from effect 2 to effect 1, and my P1 is higher than P2. So, basically, I am going from a lower pressure to a higher pressure, and therefore, we have to attach a pump in order to facilitate this movement. So, we will have some saving if we have cold feed, but we have also some expenditure because we are now pumping it. But in some sense, it will be helpful when we have, let us say, a viscous liquid. The reason being, the viscosity of the liquid will basically decrease with temperature, right? So, in the previous case, the temperature was decreasing between effect 1 to effect 2, right? So, we will have a higher viscosity that is coming out here, and this higher viscosity may be difficult to move out, right? On the other hand, in the next case, the liquid is going out from a hotter effect. So, this will have therefore a lower viscosity. So, knowing that my viscosity decreases as temperature increases, if I have viscous liquid, I will prefer that the product is coming from the hotter effect, which is effect 1 in the case of a reverse feed, and that is why we are preferring that. In the case of a forward feed, the product is coming from the colder effect. So, naturally the viscosity will be higher and we will have issues with flow and all that. Okay. So, let us now go ahead and define the variables for this problem and do an overall mass balance and then solute mass balance and then finally energy balance. So, now again just like what we have earlier, we had a feed with a solute mass fraction of xf and temperature Tf, and we again have a steam, that is the temperature Ts and pressure Ps. In the first effect, not much has changed. The condensate again has the same flow rate and same temperature and pressure condition. But rather than saying that now the pressure and temperature inside is P and T, now I am calling it P1 T1 for the effect 1, P2 T2 for effect 2 and P3 T3 for effect 3 and so on. Okay. So, now the vapor that is coming out, let us say it has a mass flow rate of V1, liquid mass flow rate L1, XL1 is the mass fraction of liquid in the concentrated product coming from the first effect, and that becomes the feed to the second effect. And similarly, V2 is the vapor leaving the second effect, L2 is the liquid leaving the second effect, and XL2 is the mass fraction in there. And similarly, V3 is the vapor from the third effect, and L3 is the vapor in the liquid from the third effect, the final product, and XL3 is my mass fraction of liquid that in the final product, right. And now, since we have 3 heat exchangers as well, in principle we can have different overall heat transfer coefficients U1, U2, U3 for the 3 effects, and different heat transfer areas A1, A2, A3 for the 3 effects. I will assume later that they are same for the problems we will do, but in general the heat transfer coefficient and the heat transfer area can be different for the 3 effects because they are different piece of equipments. So, now if I do the overall mass balance, in the first effect what is entering is F, and steam is again not mixing with the feed. So, what is leaving is my liquid stream L1 and the vapor stream V1. So, F is equal to L1 plus V1, and similarly for the second effect what is entering is L1 and what is leaving is L2 and V2, and for the third effect what is entering is L2 and what is leaving is L3 plus V3. I can again go ahead and do the solute mass balance. So, the amount of solute in the original feed is F into XF as we had earlier. Since there is no solute in the vapor, all of them goes in the liquid phase. So, from the first effect we will get L1 into XL1 of the solute, and this becomes the feed to the second effect, and what comes out is L2 into XL2. So, if I do the solute balance for the second effect, we will get L1 XL1 is equal to L2 XL2, and similarly for the third effect we will get L2 XL2 is equal to L3 XL3, right. So, in general we can write this equation that essentially are 3 equations, because I can write 3 equalities from there. Fxf is equal to L1 XL1 for the first effect, L1 XL1 is equal to L2 XL2 for the second effect, and L2 XL2 is equal to L3 XL3 for the third effect. I can go ahead and write the energy balance equations also. Again, I will make similar approximations, assumptions that we have done earlier. We will assume that the heat capacity is constant. We will again ignore the heat of solution. We will again ignore the boiling point elevation, and we will again assume that the conditions for the steam and the vapor are saturated, right. So, now for the first effect, we will have a very similar equation. Instead of T that we had in the single effect case, now I have a T1, that is the temperature of the first effect. So, this is my sensible heat change of the liquid. This is the latent heat supplied by the steam, and this is the heat or enthalpy carried by the vapor. Similarly, for second effect, this is my sensible heat change L1 into Cp into T1 minus T2. V1 lambda 1 is the what is we are getting from the condensing of the vapor from the first effect, that is heating now the second effect, and V2 lambda 2 is the what is carried by the vapor going out. And for the third one again we have a sensible heat change. The temperature is changing from T2 to T3, so L2 Cp into T2 minus T3, plus this is the energy supplied by the vapor, that is the heating medium now, and finally this is the energy or enthalpy carried by the vapor going out, right. So we have got now three energy balance equations, and similarly we will also get three heat exchange equations, right. In the first case, steam, the fresh steam is the feed, so the heat is S into lambda S that is supplied, and this is equal to U by delta T. In this case, U1 A1 into delta T is Ts minus T1 in this case. For second effect, V1 becomes my heating medium. So V1 lambda 1 is the amount of energy I get from there, and this is U2 A2 delta T, and delta T in this case is the temperature difference. V1 is at T1, the effect is at T2, so T1 minus T2 becomes the delta T. And similarly for the third effect, we have V2 delta 2 is equal to U3 A3 delta T, which is T2 minus T3, because vapor comes at T2 and the temperature of effect is T3. So T2 minus T3 becomes the delta T in the third effect. So this is the final set of equations. I have not written the property relations. Just keep in mind that those are also there for the latent heat, for the pressures, the heat capacities we can get from the property relations. But these are the most important equations now. So now we have three mass balances, overall mass balances. We have three solute mass balances. We have three energy balances, and we have three heat transfer equations or heat exchange equations. So let us see how we can go ahead and solve it, right. This is one way of solving it. So let us say V1, V2, V3 is not known to us. In that case, I can get V1, V2, V3 from the first three equations, and I can essentially use that to eliminate V1, V2, V3 from the remaining equations, right. So I will drop these three equations now, and instead wherever I have V1, V2, V3 appearing in the remaining equations, I am going to substitute for V1, V2, V3. So effectively those three unknowns are dropped from the equation because we have eliminated using the equations that we have got from the overall mass balance. So if I do that, then I have a relatively simpler set of equation. So now we can do the substitution, but in order to make things easier, what we also assume is the heat transfer coefficients are the same for every effect, and the heat transfer area is also same for every effect. So now the six equations, after substituting for V1, V2, V3, this is where we had V1 earlier, this is where we had V2 earlier, and this is where we had V3 earlier. The same V1 also came here, and same V2 also came there. So we have replaced all of that, and V1 also appeared in the fifth equation, and V2 also appeared in the sixth equation. So all these places we have eliminated. In addition, I have also replaced U1 A1 and U2 A2 with UA, because the heat transfer area coefficients are assumed to be same, and heat transfer areas are also assumed to be same, right. And then we have solute balances as usual as we had earlier, and again keep in mind that we have property relations, right. So now we have to make choice of the given variables and unknown variables. So now we have in total 6 equations here and 3 here, so total we have 9 equations. So we have to basically keep 9 unknowns in the problem, right. So everything else should be known to us, right, and those should be given in some sense, right. And again I will make a choice of a possible given values. And as I said earlier, for single effect evaporator, this choice will dictate how easy or difficult it will be to solve those equations. So let us say that the feed F is given, the mass fraction XF in the feed is given, and let us say the final product, the liquid flow rate, is given, the temperature of the fresh steam is given, the feed temperature is given, temperature leaving the last effect is given, and the heat transfer coefficient is given. So then I have total 9 unknowns remaining. And one thing you may notice here, that the solute mass fractions are not appearing in the first 6 equations, equations 1 to 6. It does not contain XF, XL1, XL2, XL3, which indicates that I can solve them separately from the other variables. So therefore, the unknown values of the mass fraction, we can say I will get from 7. It is 3 equations there, 3 equalities, right? So this we can get from 7. It's very clear because they don't appear at all in the first 6. So how can we get it from there? And the remaining 6 has to come from the first 6 equations, right? We will discuss how can we obtain these 6 from the 6 equations, but at least the degree of freedom is equal to 0 now. We have 6 unknowns and 6 equations for first 6, and then once we have figured out them, then the equations of the mass fractions are anyway separate, so we can get the mass fractions from the 7th equation, or in fact the 7th equation is essentially 3 equations, so 7 to 9 equation. Okay, so just to summarize, we have discussed how we can extend the single effect evaporator to a multiple effect evaporator. I have discussed the example of forward feed and reverse feed, and we discussed the advantages of the forward feed over reverse feed and vice versa. And then we have taken the example of a triple effect forward feed evaporator, and we did mass and energy balance equations and heat exchange equations for that case. And we have got the final set of equations that we need to solve for. In the coming class, we will do the same thing for the triple effect evaporator with a reverse feed, and then in the following classes we will see like how we can solve it numerically in addition to doing different kinds of examples on the evaporators. So with that, I want to conclude here. Thank you so much.